Welcome to this tutorial, and today we're going to be looking at using an Arduino Uno with some external EEPROM. The chip we're going to be looking at is the 24LC256, which as you can see is there's a picture of it in the introduction. Nothing particularly special to look at. If you are ordering these though, make sure you order the DIP 8 version, which you can see here, because it does come in different types. If you get the wrong type, it's going to be so small you're not going to be able to solder it. Anyway, EEPROM, electrically erasable programmable read-only memory. It works a little bit like a mini hard drive is the best way to put it. You can write some data to it, you can read data from it. However, unlike a hard drive, the amount of storage you've got is extremely small. This stores 256 kilobits, but actually that works out at 32,768 bytes, so not a great amount of data. And of course, if you're then storing integers, you're down to just over 16,000, and if you're storing longs, you can store just over 8,000. Now that might not sound like you can store a lot of information, and to be honest, if you want to do a data logging project, if you've got data coming off sensors every few seconds, EEPROM probably isn't what you're looking for. For that sort of thing, you really need an SD card. Where EEPROM is extremely good is if you've got a project that is updating certain settings. So I use this in my model railway projects, in my controllers. So I have a controller that controls all my locos through DCC, and I use EEPROM there to store all the information about the locos and all their various settings. I've got another accessory decoder that runs a turntable. Now, as temperatures change, I've got some adjusters that can make very fine adjustments to the position of the turntable exits. As those changes are made, they get updated into the EEPROM, so when the layout starts up again the next time, it knows exactly where the correct position is. So EEPROM is basically a good way of storing data that gets updated, but not data where you're going to want to sort of try and download it to something else. It's really something to do with internal settings. And to be honest, when you use just about any electronic device, when it stores information internally, it's going to be storing it in an EEPROM. So they are a very useful chip. Right, let's get into it. So if you're using an Arduino Uno, the first thing you've got to think about is, why aren't we using the internal EEPROM? Because an Arduino Uno and the Mega both have internal EEPROM built in. The problem is that the Uno only has 1024 bytes, so that's very small. You know, we've got 32 times more storage available on the external EEPROM. But there's another issue, and that is that the Uno can only rewrite the data on a specific location in the EEPROM 100,000 times, whereas external EEPROM is going to give you at least 1 million writes, so 10 times as much. Now that might not sound too much of a problem, but if you were updating some data every sort of second or so, you're actually going to wear out your Uno EEPROM within 27 hours. Whereas obviously you're going to get 10 times as long out of your external EEPROM. Now, one thing to say about that, if you are storing data endlessly, certain settings endlessly, and you do need to question why you're doing that with EEPROM, but what you can do is just keep changing the address location. So some of my projects that update quite a bit, every time the system restarts, it rewrites all the data to a new location, so it spreads the wear out around the EEPROM chip. So just something for you to think about when you are using your EEPROM. Don't sort of keep bashing away at the same point endlessly, because you will wear the thing out. So let's get on with it and start to look at how we wire this thing up. So here's our circuit diagram. As you can see, you've got the chip here. There is an indentation at this end of the chip. Make sure you get the chip the right way round or you will fry it. Okay, so this end pin here goes to 5 volts or 3.3 volts depending which board you're using. You've got your ground pin here. We then have the SCL pin, because we're going to be using the wire library. That goes to A5 on an Arduino Uno. I've got a reference on the Digital Town website to the wire library that will give you the pins for various other Arduino boards, and obviously if you're using an ESP32, just check which pins you're going to use. You then need to have the SDA pin. On this one it's going to A4, and from the SDA pin I've got a 10k pull-up resistor. So that basically connects through this wire back to 5 volts or 3.3 volts depending what you're using. You'll need that pull-up resistor or it's not going to register correctly. And then we have this VSS pin off the back here that goes to ground. Now you'll notice I'm not using 3 pins here. These 3 pins actually allow you to change the address of the chip. As standard, the chip registers as a hex value of 50, but by making these different pins live in any combination, so connect them to the 5 volts or 3.3 volts, whatever you're using, it will change the address of the chip. That means that you can alter it if it's conflicting with any other devices that you've got on the wire bus, but also it means you can have more than one of these chips if you wish. So if you needed a lot more storage, you could add more chips. And don't forget, there is also a 24LC256 version of this chip if you need twice as much storage, and I believe there's even bigger ones, but I've never used them, so I'm not quite sure on the full details of them. So as you can see, the basic circuit is quite simple, and once you've got that running, then the next job you need to do is run a sketch to make sure that it's all working correctly. So let's move on to that. So to test you've wired it up correctly, just go to File, Examples, go down to the wire library, and you want the I2C scanner sketch. I've already got it up and loaded. Basically what this does is it checks to see what I2C devices are connected. I've already loaded up, and as you can see, I've got my devices found at hexadecimal 50. So my Arduino is correctly connected to this device. So let's get that sketch out of the way and get on with some programming. So the first sketch, and again if you go to the Digital Town website, this is available for download. We include the wire library. I then set up, I define disk 1. I just call it disk 1. I just find it easier to think of it almost like a hard drive. So my chip is called disk 1 and it's given its address. I then have a function here which is the I2C scan I2C. Now that sketch that we had just looked at, this sketch here, basically I reduced all of this down to a little function and I've put it at the beginning of the script, and this means that when we go to the setup, we start obviously the serial, start the wire library, and then I do this scan. And even in my controllers that I've built, I tend to include this in my code anyway as a function, just to make sure that the device is correctly connected. Unlike the original sketch, obviously I only run it once because I only want to find out the information once, but I put it in there just to get things started. Now once I've done that, I then work through. There's just something odd about this sketch just for you to be aware of. There's nothing in the main loop. The reason I've got it all in the setup is that I don't want this sketch running endlessly, because obviously if I leave this writing endless information to my chip, I'm going to eventually wear it out if I go and write stuff every few seconds. So I'm trying to preserve my chips. Right, so what do? I've got an integer q, I've got a byte called next byte, and what I do is I'm going to call this function, which I'll show you how it works in a minute. I'm going to call disk1, which is my chip, and I'm going to move through the memory locations at q times 32, and I'm going to read 32 bytes. Now this is important because one of the things you're going to have to learn when you're dealing with EEPROM is you've got to decide where information is stored and read from. So if you can imagine, I'm going to start at location 0, because 0 times 32 is 0. I'm going to read 32 bytes of information, and then what I want to do is jump 32 bytes further along the line and read some more information. Now if you struggle a bit with the whole idea of bits, bytes and all the bits that go with it, I've included on the Digital Town website a link to a tutorial that I did on bits, bytes, integers, longs, the different data types, to give you an idea. So anyway, let's have a look at this function EEPROM read and see what it does. So if we go back up here, EEPROM read, there we go. So it takes the value of the disk, the start address from where I'm going to start reading, and the number of bytes of information I'm going to read. Now in this function it's got a warning here that the number of bytes must be smaller than 33. The reason for that is in the wire library there is a limit of 32 bytes that can be read in a single go. So there's no point putting a value in or trying to get this thing to work above that. Again, it's just something you need to think about when you're thinking about your data structure, and we'll look at that a little bit later. So what we do is we begin the transmission to disk 1. The address, because it sends data in bytes, and the address is probably going to be quite a high number. If it's 10,000, it's more than a byte. You know, a byte goes up to 256. So what it does is it sends the information as 2 bytes, a high byte and a low byte. You don't need to panic about that, but this function does that automatically for you. It then ends the transmission, and then it reads the data back, and if it's got the correct information it returns a 1. Now if we then go back to the bit of code where we called that function, so we've read the information, and then what it's going to do is, while there is data available, it's going to read through the sets of bytes. Now I'm just going to load this thing up and you can see how it works. Now the EEPROM that I've got, that I'm doing these tests on, has already got stuff on it, just so that you can see some information. I've pulled it out of another project, so it's got all sorts of stuff on it. So let's just wait for this thing to compile. Right, okay, we've seen some data flashing up there. Let's scroll up and see what we've got. Scroll past all of these bits which are nothing to do with this. Here we go. So q equals 0, and then it's read the first 32 bytes then goes to 1. You'll notice now a value of 255. That's because it's actually looking at a part of the EEPROM that's never had any data written to it, and the default value is 255. So you can see in that first section I've written various values. Then we've got a section that's not used. Then we've got a section later on where I've stored data again, and you can see the different byte values coming through and being displayed. Now if we continue to go down the code, because obviously reading is one thing, but we want to write information. So what I've done here is I created a function called EEPROM write. Again, you've got to tell it which disk. This is important because I could have a number of EEPROM chips, and also of course there could be other items on the I2C bus. Q is a value that I'm going through, so it's going to write to location Q, and it's going to put a value of Q in. Maybe I should have used different values, but I was in a hurry when I wrote this. So here is what it then does. So if we go to the EEPROM write, it receives the disk, the address I want to send the information to, and the data I want to write. So again, it begins the transmission to the disk. It then takes the EEPROM address that we're going to write to, a high and a low byte, and then it writes the data that comes in here. Now that data needs to be a byte. That should say, that should be byte there. Sorry about that. So it reads that byte of data. It then ends the transmission, and I've put a slight delay in. That just allows it to write the data to the system. Then what it does is it reads that information back. Now, as I've already compiled and uploaded this, we see that I'm writing to the first 5 bytes, then it reads back from the first 5 bytes, and we get the values for Q 0, 1, 2, 3, 4. Now, at the moment, we're only writing bytes. But obviously, there are times when you're going to want to write an integer and even a long. And that's where you have to start to think about a little bit more carefully about how you write your data. So we'll now move on to the second sketch. Right, so here is the second sketch that I've put up as an example. Now it just follows on from the previous sketch. So the previous sketch we just looked at how to write these various bytes. Now what we're going to do is start looking at writing an integer, and we're going to write it to a specific address, and I've decided to write it to address 10. Could have been anything, could have been 10,000. But an important thing to think about, an integer is 2 bytes long. So when it writes this, address 10 and 11 will get used. Now this is important for you to think about, because if you can imagine, if you wrote an integer to address number 10 and then you wrote an integer to address number 11, when you read the data back, the integer that started at address number 10 would have been corrupted by the integer that starts at address number 11. What you'd actually need to do is write the first integer to address 10 and then write the second integer to address 12. So you just need to be aware of that. So then I've put my integer value in, and then I've called a new function that I've written, which is EEPROM write int. And again, disk address, the address that I want it sent to, and the integer value that I'm sending. Now we'll skip back up the code to, where are we? Here we are. We're going to write our integer here. So again, we're receiving the disk, the address, the data. This time it is correct, it is an integer. Now what I've done is I've created 2 bytes, first byte and a second byte. Again, if you don't understand how an integer is put together, obviously we work in base 16 rather than decimal. So the way it works is the first byte, I'm using the what I would call the higher value, and then the second byte is the lower value, and I'm going to serial print out what those two values are. To put them back together, it's the first byte times 256 plus the second byte. So it would be a bit like the value of 24 in decimal. It's 2 times 10 plus 4. It's that sort of thing, except we're doing this in hexadecimal, so we've got a value of 256. And then what it does is it calls that same function, EEPROM write, and it writes the first byte to the EEPROM address. It then writes the second byte to the EEPROM address plus 1. Now, in the serial monitor, what I've done is we're writing a value to that address. The value that we're sending through our integer is 12345, and that means that our first byte has a value of 48, the second byte has a value of 57. If you multiply 48 by 256 and add 57, you get 12345. And what I then did to prove that is I then have a function that is reading back the integer. So what I'm saying is I want to go to an address and I want to get the integer value, my int, and obviously it prints it out, which is what has gone on here. But if we go up to the actual function, let's have a quick look at how it works. So we're going to read, this time we're going to read from the address that is stated. Again, I have my first byte and my second byte. So we begin the transmission. We're asking for, we're going to the correct address. I'm asking for 2 bytes from this particular disk. So I just want 2 bytes, and I read it. The first byte that I read back is the first byte. My second byte, again, I do a second wire read to get the second byte. The return value is then my first byte times 256 plus the second byte, and that is the value that gets returned back to my original function, and hence I then get, where are we? Back in my setup. There we go. So now I've read back my integer and I've printed it out, and we can see that's what I get there. Now, as well as doing an integer, and I do use integers quite a bit because on model railways, if you're using DCC, decoder addresses are integers. However, I've not used longs for anything. I've never had a use for them, but I decided I'd just give you an example of how you would write a long. This time I'm writing it to address 20, and obviously my long is a much bigger number. This time you have to remember that it's going to take up 4 bytes. So again, this time, if you wrote the first item to address 20, we're going to use all the values up to 23. So if you wanted to write another long, you would have to start writing at 24. So I've got again an EEPROM write. It works exactly the same as the previous function, and then I'm going to read my long back. So let's have a quick look at those functions and see how they work. So the EEPROM, where are we? There's EEPROM read long. Where's EEPROM write long? There we go, EEPROM write long. To try and make this understandable, I created 4 bytes. You know, realistically you would do this in an array, but I've done this just to try and show how this is done. So you've got the 4 bytes that are coming from my EEPROM data. And here we have the bit of code that gets the first byte, second byte, third byte, and the fourth byte. I've then serial printed them out just so that we can see them. So our number 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. The first byte 73, 150, 2, 210. Then again I write to the EEPROM the address for the first byte, address +1, second byte, address +2, third byte, address +3 for the fourth byte. That's how that works. And then obviously reading it back is exactly the same as the reading the integer. God, losing track of it. There we go. So again, just to make it easier for you to see, I've split it up again into the different bytes. We send a request to the disk. This time we're asking it for 4 bytes because we have stored our data over 4 bytes. I've then written out how the 4 bytes are split up, and then this is how we work out the return long. So it's the first byte multiplied by that number, second byte by that, third byte by that, plus the fourth byte, adds it all together, gets the value and returns it, and lo and behold, it gives us the correct value. So that is how you would read and write integers and longs if you need to do it. Now the next bit we're going to look at is data structure. Now many years ago I worked as a programmer, and we reckoned the most boring subject you could ever lecture on was databases and data structure, but unfortunately when we're dealing with EEPROM we need to think about data structure. Now the sketch that you see here is for a controller that I've built for my DCC model railway. I tend to put my EEPROM functions in a separate tab, just keeps my code cleaner. And this is where I want to start looking at data structures, because it's worth planning these things. You've got to think about it. So the way my data structure works on this thing is the first 20 bytes are reserved for data that is used by the controller for what I would call system information. So the locos that are being the loco that's being controlled by the left controller, loco that's being controlled by the right controller. I've got a remote system as well, so there's another controller. I've reserved some stuff. Again, it might sound weird, but it's worth reserving things rather than having to add them in later. My controller has a real-time clock as well as a clock that can be accelerated. So when I switch it back on, because I run to a timetable, I want to know where I was last time. And so I store the current layout, year, time, all of this information gets stored so that it can work that out. Now that's only using 20 bytes, and when I start up the sketch, it reads that information out of the EEPROM straight into arrays that are stored within my code. So that's that bit. But I also store data on my locos. So if you're running a DCC model railway system, your decoders have an address, which is an integer. So in my system, each loco has an ID. The way I've built my system, because I'm only using a byte, I can only have 256 locos on my layout. In my dreams that I could ever afford that much, but you know, it's a limit that I have. The decoder address is an integer, so it requires 2 bytes, and then each decoder has a number of functions, so I allow positions 3 to 31 for function data. Now you may notice that that means from 0 to 31 is exactly 32 bytes. And if you remember when I talked about the limitations of the system, the maximum amount of data that you can call in one go is 32 bytes. It's worth thinking about this as you build your systems, to think in blocks of 32 or certainly logical numbers. Now, one of the things that I do is that first set of data starts at position 0 and goes to 19. With the loco data, I then have a gap and I jump to position 1000, and as you can see, it's storing various data based on that address. I then have loco names. Obviously, although those are letters, they're stored as ASCII numbers that can get converted back. So again, you've got the loco ID. My controller allows for a 20 character display of the loco name, and 21 to 31 are reserved, and that gives me, yes, you've got it, another 32 bytes. And you'll notice I make a note in here that the start position for that data is at 10,000. Now, the reason for the big gap between them is that if you've got 100 locos at 32 bytes per loco, you need 3,200 bytes. If I upped it to 256 locos, lo and behold, I will need, something like 9,000 bytes of data. Therefore, the one starts at 1,000, and then the next set of information starts at 10,000. I then allowed some space going on to 20,000, which is where sort of turnout information, point control, is listed in there. But what I want you to understand here is that when you are using EEPROM, if you're going to start storing a lot of information, it's worth sketching out where you're going to store that information on the EEPROM and start working out some functions to read and write to the correct locations. So I think that is about all of it for this tutorial. EEPROM is extremely useful. Obviously, it's not the be-all and end-all of everything. As I said before, if you're going to be logging data, lots of data over a long period of time, it's not the right component to use. But for storing data and settings in a project, it is absolutely fantastic to use. It's very fast, very, very cheap. The chips are near bulletproof, and I'd recommend it to you. Anyway, if this has been useful, please click the like and subscribe, and don't forget there will be a link in below the YouTube video that will give you a link back to the full tutorial. There's the circuit diagrams, the two sketches, everything is there. So thanks for watching, and click the like and subscribe if it's been useful. Bye for now.